Okay, so we can start. It's great to have Yuen from Columbia University. It is great things in quantum computation and complexity theory. And today we will talk about unified complexity and the Uhlmann Transformation Problem.
Thanks, Ron. Hi, everyone. So I think we need this. Yeah, so today I'll be talking about some joint work with John Bastanja, Yuval Efron, Alex Barendla, Tony Metker, and Lowen Chien. And I'm going to try to not assume any quantum background. So, throughout this talk, if anything gets confusing, feel free to just stop me and ask. But actually, just to get a sense, like how many of you have some exposure or familiarity with, basic quantum information or quantum computation? Okay, so maybe like a little less than half. Not an issue. So before I get into explaining what this jumble of words means, I want to sort of step back and give sort of a high-level, big picture motivation for what I think is a need for what I call a fully quantum complexity here. So today, quantum complexity theory has been well studied for 30 years or so, at least. But we can think of it as the study of models of quantum computations, solving problems that have classical inputs and outputs. So some examples of problems that people thought a lot about over the last 3 decades, you have like factoring, right? This is a problem where you have an input, which is an integer n, and the output is a prime factorization of n. And so it's a classical input, classical output. Here's another problem that's a little more recent that people have been interested in, which is random circuit sampling. Here you get as input a description of a quantum circuit, C, that's drawn from some distribution of circuits. And the output is a sample, which is a bit string, sampled according to the output distribution of this quantum circuit. Okay. So we think that you need a quantum computer to be able to perform this sampling task. But fundamentally, the inputs and outputs are quantum. Here's one that's inspired by or motivated by quantum physics, which is this ground energy problem. This is a problem where you're given as input a description of a local Hamiltonian H. So local Hamiltonian, you can think of it as some description of a physical system. And the output is the estimate of the minimum energy configuration, the minimum energy, which is just a number of this Hamiltonian. Okay. And I think it's, this framework has been very interesting and very helpful because by thinking about these problems, we can, compare, we want to compare the capabilities of quantum computers versus classical computers, right? So that's why we think about problems with classical inputs and outputs. Okay, but, there's a whole other class of computational tasks that you can think about, which I'll call inherently quantum tasks. And these are tasks that you might be interested in, one day in the future when everyone has a quantum computer, people are sending quantum information back and forth to each other. Here are some examples. So one is ground state preparation. This is a problem that has a classical input. So again, you get a description of a local Hamiltonian. But now the output is not just a number, but a collection of quantum particles that are in the ground state of this local Hamiltonian. So now when solving this task, you actually have to output a quantum state. And this is something that just doesn't make sense for a classical computer to do, right? This is a quantum only thing. Another example would be state tomography. Here you get as input a quantum state. And you have to output a classical description of that quantum state. Right? This is known as the tomography problem. An example of a problem where you have quantum inputs, quantum outputs, error correction. So you get as input a noisy quantum code word, and you want to correct it to the nearest pristine, noise-free code word. And as a last example, here's something a little more exotic, but has been of deep interest to people working in high-energy physics and theoretical physics recently, which is the computational task of decoding entanglement from the radiation of a black hole. Sounds very esoteric and sort of a fantastic thing, but this is something that they've been thinking about as a, to help understand resolutions to this black hole information paradox. This task is, you take in this radiation from a black hole, which is some highly entangled quantum state, and you want to output some other quantum state. Okay, so here are all examples of tasks that are inherently quantum. And you can naturally ask, what is the computational complexity of solving any one of these things? Right. So currently, I claim that it's kind of awkward to study these tasks in quantum complexity theory as we know it today. And the reason is most of the techniques that we have about reasoning about computational problems, even in quantum complexity theory, come from classical complexity theory, right? So, we have all these complexity classes like BQP and QMA. And these complexity classes are our main way of organizing and classifying different problems. But again, these complexity classes are defined only in terms of classical input, classical output tasks, so decision languages. So in order to, to be able to better reason about some of these tasks that I just described, like, finding the grounds, preparing a ground state of a Hamiltonian, it'd be useful to develop some, framework or fully quantum complexity theory where we can naturally talk about the complexity of these problems. Okay, so, if we were to design such a new framework, this new language, what would be some of the goals? And the goals would be very similar to the goals of, traditional complexity theory. So, first you'd like to identify collections of natural computational tasks that occur throughout the sciences, right? So, you look in condensed matter physics, high energy physics, chemistry, cryptography, optimization, and so on, and you look for examples of natural tasks that people want to do, but they involve quantum inputs and/or quantum outputs, right? So once you've collected all these natural tasks, then you want to, come up with reductions between them. You want to somehow relate them to each other. You want to classify them according to what sort of computational resources they need. Maybe identify complete problems and hopefully prove separations, right? It's the holy grail of complexity theory. Okay, so that's sort of the high level motivation, high level background. And what I'll describe in this talk is an illustration of these goals. And I'll do that by talking about something called the Uhlmann Transformation Problem. So here are some quantum tasks that I want to think about in particular. And they kind of come from all over the place. So the first one is the task of breaking the security of a quantum bit commitment scheme. A bit commitment scheme is a cryptographic concept. Basically, you want to capture the idea of being able to put a message in a sealed envelope and give it to someone. But you want to do this now in the quantum setting. And the task here is to try to, essentially break the seal of this quantum envelope, right? And I'll get more into this later, but this is one task. Here's another one that comes from quantum Shannon theory or quantum information theory. And this is one where you want to communicate quantum information. You want to send qubits over a noisy quantum channel, right? So you take in some quantum information in the form of the state psi, you encode it, you send it through some noisy channel, it might get corrupted, it comes out the other end, and you want to decode and recover the original information. So this is a very natural task that you might want to think about. And that's, a noisy channel communication. And again, this exotic example of a task where you want to decode the Hawking radiation from a black hole. Okay. So all of these seem pretty different, like, they come from different areas of science. What do they all have in common? It turns out the complexity or the difficulty of performing each of these tasks is exactly characterized by this Uhlmann transformation problem. So you can understand the hardness of all of these through this lens. Okay, so I have to explain what the Uhlmann transformation problem is, and let me just explain quantum mechanics in one slide, or at least the relevant bits. So a pure quantum state on n qubits. So you think of, you have n quantum bits, particles. The state of this is described as a 2 to the n dimensional complex unit vector. And we use this notation to denote a pure quantum state. All right, so now we can think about quantum states on, say, 2 systems. So let's imagine you have 2 n qubits now. Okay, and the joint state of these 2 n qubits can be entangled. And we divide sort of the first half into a system A, the second half into a system B. And we say that it's entangled if it cannot be written as a tensor product of 2 pure quantum states, one on system A and one on system B. Okay. So intuitively, it sort of means that, you know, these 2 halves are correlated in some way. And in fact, the correlations are stronger than what you can get from classical correlations. They're quantumly correlated. Okay. If you take a entangled state, say on systems A and B, right? Overall, the system can be described as this, you know, 2 to the 2n dimensional unit vector. But now you say, well, let's look at system A. Let's look at one half of it. How can I describe the state of this first half of system A? And by definition, it cannot be described as a pure quantum state. There's no unit vector that describes the state of these first n particles. But instead, it's in what's called a mixed state, rho sub A, and that it's just a probability distribution over pure states. Okay. So we say that the marginal state of this entangled state is a mixed state. Okay, fine. The last concept here is, you know, now we should talk about how states, quantum states evolve over time, and they evolve through unitary matrices. So unitary matrices are, in linear algebra, they map unit vectors to unit vectors. And so they transform quantum states. And now since we're thinking about entanglement, if you have a unitary matrix that acts on this entangled state, but it really only acts non-trivially on the second half, say U sub B, then this unitary is what's called local, right? It's really only doing something. It's just transforming this entire state by only acting on the second half of the system. Okay, so that's all the quantum mechanics that we'll really need to know for this talk. So using this, now I can define or describe Uhlmann's theorem. So let's say you have 2 entangled states, psi 0 and psi 1. They're entangled on systems A and B. And they have the property that if you look on the first half, the system A, the mixed states corresponding to these 2 quantum states are identical. Okay, so these 2 states are not the same, but if you just restrict yourself, like you can think of it as like the marginal distribution looks the same on the first half. Then Uhlmann's theorem says that there exists a unitary, a local unitary only acting on the second half, system B, that transforms the first entangled state to the second entangled state. This is a fundamental fact in quantum information theory. And it says this gives you it tells you when 2 entangled states can be transformed locally one into another. And it just requires that part of the entangled state looks the same. Okay, so just to give you a picture, you have a bipartite entangled state, psi 0, and they both look the same on part system A. Alice can run a quantum computation, perform a unitary transformation only on the second half, and it becomes psi 1. So that's a depiction of Uhlmann's theorem. So this is just a mathematical fact. There always exists such a unitary, provided that psi 0 and psi 1 satisfies these conditions. But we can think of it also as a computational task, right? So this Uhlmann transformation problem, it's what I call a unitary synthesis problem, where the goal is to apply an implicitly specified unitary transformation to a given quantum state. So what's the input and output behavior of this problem? So the input is you're given circuit descriptions of 2 entangled states, psi 0 and psi 1. right? That have the same marginal state on A, right? I give you a description of a quantum circuit where if you run the quantum circuit at the end, you will have psi 0, and for the other circuit, you'll have psi 1. And then separately, you're given a collection of particles that are on system B. So I'll call that state theta B. So just to make sure we understand, these two states psi 0, psi 1 are on 2n qubits, okay? But you're given classical descriptions of them, right? You're given classical because you sort of just write down on a piece of paper what the quantum circuits are. And then separately, you get in quantum form this state theta B, which is on n qubits. Okay. And this Uhlmann transformation problem is you're supposed to apply the Uhlmann transformation U corresponding to the first two states, psi 0, psi 1, on the quantum state theta B and transform that. Any questions about the definition of this problem? Okay, so it's a computational task. How hard is it to solve, right? If you were to write an algorithm to try to solve this unitary synthesis problem, how many steps would it take? Right? How much memory would it require? And you can ask, is there a polynomial-time quantum algorithm that can accomplish this? And it's not too hard to see that under reasonable complexity assumptions, there does not exist a polynomial-time algorithm for it. So in particular, if you assume the existence of what's called an injective post-quantum one-way function, then you can rule out the existence of polynomial-time solutions for this. What post-quantum means is that the one-way function is secure against polynomial-time quantum adversaries. So let's see how that works. So fix an injective function f, and it maps n bits to r bits. So r has to be at least n if this is injective. So I'm going to define the two entangled states, and these states are on n plus r qubits. So the first state, psi 0, is going to be a superposition, okay, of all n-bit strings x. So the first register is going to store the bit string x. And then the second register, this system B, is going to store the evaluation of this injective function f of x. Okay, great. So this is a superposition of input and output pairs of this injective function. Psi 1 is going to look very similar, except in the second register, you don't evaluate the function f, you just have a copy of x. And maybe you add in with some zeros because r could be greater than n. Okay, so if you do the math, you can show that because of the injectivity property, the marginal state of these two, of psi 0 and psi 1, looks the same on system A. It's just a uniform distribution over all n-bit strings. So by Uhlmann's theorem, there is some local transformation acting only on the second part, on system B, that maps psi 0 to psi 1. But what does that mean? And you sort of think through it. It actually means that if you take the unitary and apply it to the state f of x, which is a bit string, it will return a pre-image, well, the unique pre-image of f of x, which is the input x, for all possible x. And this is not something you're supposed to be able to do, to find a pre-image of this of a general one-way function. This is why we don't expect Uhlmann transformations to be easy to perform. Okay, so you say, all right, well, now we have some evidence that this Uhlmann transformation problem is hard. Okay, can we come up with some upper bounds, right? So for example, now imagine that in some crazy world, one-way functions were all invertible in polynomial time. Does that mean this Uhlmann transformation problem can be synthesized or implemented in polynomial time? Right? That'd be pretty cool, right? You somehow would have a characterization of how hard this unitary synthesis problem is. And this is in fact an open question. And it's unclear whether having the ability to solve any classical decision problem is sufficient for efficiently solving the Uhlmann transformation problem. Imagine I told you, I give you an oracle to solve the halting problem, right? It's not possible to solve the halting problem, but imagine that I gave you an oracle for solving it. Could you use this to implement, to solve the unitary synthesis problem? It's actually not clear. And the conjecture is that it's not possible, or at least I conjecture. So for any classical oracle O, using it, you cannot use it to solve the Uhlmann transformation problem with the quantum computer in polynomial time. And why is that, right? Like, the ability to solve the halting problem is this fantastical ability. And really, it's something called the no cloning theorem that makes this unitary synthesis problem fundamentally different from classical computation tasks, right? So the input to the unitary, to the Uhlmann transformation problem, there's two parts to it, right? There's the classical part, which is the description of psi 0, psi 1. But then there's also the quantum part, which is this theta b, this state that you actually want to physically transform. And the no cloning theorem in quantum mechanics says that in general, given one copy of a quantum state, you cannot make two copies. Okay, so an algorithm that's trying to solve the Uhlmann transformation problem does not have a classical description of the output it's trying to produce, right? Just fundamentally cannot have it. Because it doesn't have a classical description of the input it's trying to transform. Right? It just gets a bunch of quantum particles. So for that reason, it kind of gives you a sense that classical oracles don't help you solve unitary synthesis problems. So this is, sort of another piece of evidence that suggests that you need some new framework to think about how hard these things are. Okay, so here's maybe sketches of what such a framework would look like. So here's what I call unitary complexity theory. We want to sort of talk about the complexity of unitaries on their own terms. So let's define a unitary synthesis problem generically as just a family of unitary matrices, U sub x, indexed by binary strings. So X is sort of like the instance. It sort of tells you which unitary you want to apply. And you can also think about like promise problems where you only want to define it on a subset of strings, but let's not worry so much about that. So we can define this Uhlmann transformation problem as a set of unitary matrices. And here we'll have a promise where if this bit string X happens to represent a classical description of state psi 0, psi 1, where the marginal state on the first half looks the same, right? Satisfies Uhlmann's theorem. Then this U sub x should be the corresponding Uhlmann transformation. Right? This is kind of like the unitary analog of a language. It's right. So there should be extra words to say like this is the minimal transformation to make sure that it's. So there's some details to make this well defined. Good question. Okay, so we can define unitary synthesis problems. It's just a family of unitary matrices. And now let's define what it means to solve or implement a unitary synthesis problem. So a quantum algorithm implements unitary synthesis problem U if given input X, which is the classical part, and then the quantum part theta, it applies U sub X to theta. It outputs this quantum state. All right, and now we can start to define unitary complexity classes. It's just a collection of unitary synthesis problems. So natural classes you might first want to define, let's call it unitary BQP. This is a set of all unitary synthesis problems where you can implement them using a polynomial-time quantum algorithm. Analogously, unitary P-space is a set of all unitary synthesis problems where you can implement them using a polynomial space quantum algorithm. Okay, so now we have some language now that we can use to start reasoning about this Uhlmann transformation problem. So just to repeat the reasoning we had before, assuming the existence of injective post-quantum one-way functions, this Uhlmann problem is not in unitary BQP. What about some upper bounds? You can show that you can solve it using polynomial space. So there's a unitary p-space upper bound for this problem, so it's not arbitrarily difficult, right? And then you can ask, okay, can we actually precisely pin down a natural complexity class for which the Uhlmann problem is complete? Right. I mean, you can always define, all right, some complexity class for which, by definition, Uhlmann is complete for, but that's not so interesting. But it turns out there's a natural one, or I think a pretty natural one. And it's defined in terms of an interactive proof complexity class. So what's an interactive proof for a unitary synthesis problem? And I'm not going to go so much in the details here, but I'll just kind of like sketch the scenario. So here you have a polynomial-time quantum verifier. It wants to solve this unitary synthesis problem. So it gets as input x, comma, some unknown state psi. And it can't do it by itself. So instead, it wants to talk with an all-powerful quantum prover. So it shuttles qubits back and forth. And at the end, if this verifier accepts, it should be able to output the solution to this unitary synthesis problem, actually apply the unitary. So that's this model of interactive proofs for unitary synthesis. We can also define a notion of zero knowledge for such protocols. This is roughly where the verifier state at each round in this protocol can be efficiently simulated without the help of a prover. And so if you've seen zero knowledge before, then this is should be very analogous. All right, so the theorem that one can show is that this Uhlmann transformation problem is complete for the unitary complexity analog of the class statistical zero knowledge. Right, so any unitary synthesis problem that can be solved in zero knowledge using this kind of interactive proof can be reduced to this Uhlmann transformation problem, and vice versa. Right?
So the prover knows the quantum state.
The prover can know the quantum state.
Yeah, for us as many copies as.
Oh, okay. So right. What the prover? Okay, so this is what this average comes in. So this only holds on the average case. What this means is this state is sampled from some distribution, and the prover knows that distribution, but he doesn't know exactly what this.
The interactions are they quantum or classical?
The interaction is quantum. Okay, so now we're starting to put together pieces of this unitary complexity landscape, and we have some basic classes like unitary BQP, unitary p-space. The Uhlmann transformation problem is somewhere in between, and it's complete for some notion of zero knowledge. So that's pretty interesting. All right, but now let's start relating it to other interesting quantum tasks. So let's talk about the connection between the Uhlmann transformation problem and quantum cryptography. Already, the fact that Uhlmann is complete for unitary SEK gives you some indication that it's related to cryptography. But here's another connection. So let me talk about commitment schemes, which I mentioned before. So in general, a commitment scheme, this is a concept that comes from even classical cryptography. This is a protocol executed between two parties that don't necessarily trust each other. So let's call them committer and receiver. And it's, like I said, it's, a commitment scheme is the cryptographic equivalent of putting a message in a sealed envelope that's opened later. So there's two phases to a commitment scheme. There's a commitment phase. So the committer gets some message M. The message M here is classical. And then it interacts with the receiver. After some dialogue, the receiver is going to have a commitment C, and think of this commitment as storing the message M in some hidden fashion. So the hiding property of a commitment scheme means that the receiver at this point still has no idea what message M is, right? So so far the message M is not known to the receiver. In the second phase, the committer will then reveal the commitment and reveal this message M, okay? And the receiver will reject if the opening is inconsistent with the commitment. Otherwise, it accepts, right? So, this is sort of the analog of opening up the sealed envelope. And the binding property of the commitment scheme means that in the second phase, the committer cannot have opened to a different message M prime than the original message, right? He can't suddenly, in between, change his mind about what message he wants to suddenly reveal to the receiver. So this is a commitment scheme, super useful. It's a very basic object in cryptography. And, in the 90s, people were very interested in the possibility of obtaining quantum protocols for commitment schemes. So, people realized that using quantum protocols where you transmit qubits back and forth to each other, you can obtain information theoretically secure key distribution, right? So you can do encryption, information theoretically secure. You don't need to assume that any computational problem is hard, right? This is known as quantum key distribution. And this was very exciting. And people said, well, what about other cryptographic primitives? Can we also obtain security for these unconditionally? But it was shown by Lo and Chow in '97 that for quantum bit commitments, you can't obtain this unconditional security, right? You have to rely on some computational assumption, even if the protocol uses quantum communication. So how does their proof work? It actually uses the Uhlmann's theorem. So they say, suppose that you had a quantum bit commitment scheme, right? So there's two phases, the commitment and reveal phase. Let's look at the state of the committer and receiver right before the reveal phase. Right? So it's just, you look at the committer and receiver, they've maybe exchanged qubits or something. The state of the whole system can be described by psi b, where b is the bit that the committer wanted to commit to. So if this bit commitment scheme was secure, then it satisfies the hiding property, at least. And what that means is the marginal state of psi 0 and psi 1, from the point of view of the receiver, looks the same, right? That means the receiver cannot distinguish between bit 0 and bit 1. But then you can just apply Uhlmann's theorem, and the committer can apply a unitary only acting on his qubits, his system, to switch. Maybe he originally committed to bit 0, so they're in this state. But then he can apply a local unitary to just transform the whole system from psi 0 to psi 1. But then, he would have essentially changed his mind. So then when he runs the reveal phase, he would have convinced the receiver that he actually committed to bit 1, even though that's not what he did. So he's broken the binding property of the commitment scheme. So, just to say it succinctly, if the Uhlmann transformation problem is in unitary BQP, right? You solve it in polynomial time, then all quantum bit commitments are insecure. So you need some sort of computational assumption. And it's not too hard to see that you can actually just run their proof in the reverse direction. Suppose you had a hard instance of the Uhlmann transformation problem, right? So this is a pair of states, psi 0, psi 1, that look the same on one half of the system. You can use these states to create a secure quantum bit commitment scheme, okay? Where it has the statistical hiding property, meaning that no receiver, regardless of how powerful they are, they can distinguish between bit 0 or bit 1 before the reveal phase. And it also has a weak notion of computational binding. So it just says that no polynomial time committer can essentially change his mind, change the commitment with probability better than 1 over 1 minus 1 over some polynomial. All right, so this is maybe not such a strong notion of binding, but it's non-trivial. But it turns out that that's enough to actually get all the way to a strong commitment scheme. So something that we've recently shown is that if you have a quantum commitment scheme with this weak binding property, right, says that you can't change your mind with, probability essentially 1, then you can boost it to have a strong binding property, meaning that no polynomial time adversary can change his mind with even negligible probability. Furthermore, there's also prior work that shows that these quantum commitment schemes, and you can have these different flavors of, are you assuming that the hiding property is statistical and the binding property is computational, or vice versa? These two flavors of quantum commitments are equivalent, so you can, in a black box way, transform one to the other. So that's sort of says that all commitment schemes are roughly equivalent. All right, so putting everything together, the arguments that we've seen implies that this Uhlmann transformation problem not being solvable in polynomial time. There's some caveats that I won't get into. That this is equivalent to the existence of a quantum bit commitment scheme. Okay, so this is a strong connection between this Uhlmann transformation problem and a fundamental object in quantum cryptography. Okay, so now let me turn to connections between Uhlmann transformation problem and some other topic. I'll talk about quantum Shannon theory. So here's a famous result in information theory, which is known as the noisy channel coding theorem. So imagine that you have a noisy channel. For now, it's classical, so let's call it N. Shannon proved that the maximum achievable rate of communication over a noisy channel is given, which is called this capacity, is given by this beautiful formula. It's characterized by something known as the mutual information between the input and output of a given channel, maximized over all possible input distributions of messages to this channel. Okay. Wonderful theorem. It sort of exactly pins down, like if you're to use this channel many, many times, what's precisely the maximum rate of information that you can reliably send through this channel. Okay. And fast forward many years later, people are naturally interested in a quantum version of Shannon theory, right? And this is this very broad subject where you study the quantification and compression and transmission of quantum information. Similarly, a fundamental problem is to understand the achievable rates of communication over noisy quantum channels. But unlike this, the beautiful situation that we have in the classical case, we don't have as neat an understanding of the capacities of noisy quantum channels. And in fact, there's many different notions of capacity and models of communication that one can consider, and they're all interesting and they're in different ways. And in very few cases do we have a formula as neat as this. So this is an active area of study. But let me talk about one particular model for which we have a nice answer for, and this is called entanglement-assisted communication. So here, now let's think about a noisy quantum channel, right? So you send a quantum state through, maybe it gets corrupted, comes out the other side. And what we would like to do is devise for this channel encoding and decoding schemes to protect some input information that we want to send across. And this is entanglement assisted because now we allow the encoder and decoder to share an additional entangled state that comes as input to possibly help it achieve a higher rate of communication than if it didn't have entanglement assistance. So it's important to note that this entanglement does not interact with the channel. So you can assume that this entanglement is pristine. There's no errors in it. And it's a resource that the encoder and decoder can use to help correct errors. So this is the model. Okay. And you can define what I'll call the one-shot capacity, entanglement assisted, of a noisy quantum channel. And this is the maximum number of qubits that you can send using some encoder and decoder, where at the end, when you get the state, it achieves fidelity, the accuracy 1 minus epsilon, right? How close is the output state to the original input state? Using some amount of pre-shared entanglement and one use of this channel. So the one shot just refers to the fact that I only get to send information through n once.
Entanglement is not bounded.
Entanglement is not bounded, yeah. So it can as much entanglement as you want. Okay. So this is the model. So I just talked about one-shot capacity, but then you might say, well, what if I have many uses of the channel? Maybe having many uses, I can asymptotically get some sort of rate. And so here we can also define the asymptotic or just capacity of an entangled-assisted capacity of the channel. And like I said, it's one of the few channel capacities in quantum Shannon theory with what's called a single letter formula characterization. What I mean by that is, and here's the theorem that was proved in 2002. For any channel, quantum channel, the entanglement-assisted capacity has a very similar formula to what Shannon proved in 1948. It's 1/2 the quantum mutual information between the input and output, maximized over all possible quantum input states to the channel. So, and this is called a single letter formula because you're only, the way you compute this quantity only relies on essentially one copy of the channel, even though you're really reasoning about the asymptotic rate. In many other channel capacities, the best characterization that we have for the capacities really relies on taking a limit of, in this formula, you might have the limit as n goes to infinity, and it seems unavoidable for other types of capacities. But here we have a single letter formula.
Are there examples of capacities where you know it's not to be computable?
I think that's an open, yeah.
Follow from there. Even that something we know compute here now.
Yeah, I don't think anyone's formally studied that. So, yeah, I think it's related, maybe related to the stuff you've looked at, the information complexity. Anyways, so anyway, I should just mention a major open question in quantum information theory is if you take away entanglement assistance, is there a single letter formula for the capacity? It's not known. I think people are divided on whether there should be a single letter formula or not. So, okay, so that was the information theory. And, but now you think, all right, in the real world, I actually want to transmit something through some noisy channel. And of course, you want to do it in an efficient way. So now you're forced to confront issues of computational complexity. Suppose I hand you a description of a quantum channel, noisy channel N. Can you achieve this capacity, the optimal capacity, with a polynomial-time encoder and decoder? So for channels of the form, N, but then you take many copies of it, there is an optimal protocol that achieve a rate that's close to this capacity number. That's just, I'm just saying just by definition. But is this optimal protocol performable in polynomial time? And for this question to make sense, I should really restrict my attention to channels that are computable in polynomial time, right? Because it's easy to construct examples of channels that do some exponential time computation inside, and of course, that should scramble your information in a way that's hard to decode. But let's restrict to channels that you can actually efficiently implement, right? And so this gives rise to the following computational task, right? I say a pair of algorithms, encode and decode, solves the entanglement-assisted noisy coding task with some error for a specific channel N, if for all input states psi that have some number of qubits that's determined by the one-shot capacity, you can basically encode it, send it across a channel, and decode it. And of course, you're allowed some pre-shared entanglement. And at the end, you recovered epsilon approximation of the original state, right? And if this holds for all states side, then that means your encode and decode algorithms are good. You solve the task. All right, so here's the theorem that connects it to the Uhlmann transformation problem. If Uhlmann is in unitary BQP, this is equivalent to this noisy channel coding problem being solvable in polynomial time for channels that are of the form n tensor k, meaning you're allowed many copies of the channel, right? Essentially, achieving capacity is equivalent to the Uhlmann transformation problem being efficiently solvable. And let me just sort of give some cartoons of how you prove this equivalence. So one direction, so if Uhlmann is in unitary BQP, then you can actually come up with a polynomial time encoders and decoders. Here's how they what they look like. So the encoder here is going to pick a random circuit of polynomial size, and it's going to apply this circuit to the input state that you're trying to send across the channel, and also this pre-shared entanglement. So actually, the encoder is kind of dumb. It's just scrambling all its information and then splitting off some number of qubits to send across the channel. That's what the encoder does. So it's just going to apply this random circuit to the input state and this pre-shared entanglement, send it across. What does the decoder do? It's going to apply an Uhlmann transformation. Okay. So it's going to apply some unitary U that's defined in terms of some states alpha 0, alpha 1, which I'll describe in the next slide. And it's basically going to recover the original input state. So what is this alpha 0, alpha 1? So now this is something that is sort of occurring in the heads of this. This is not actually what's happening in the real protocol, but it's just sort of we're describing circuits to compute these states. So alpha 0, the first state, is going to be, basically two entangled states, so phi. And it's going to apply the same random circuit R to both of them, or to both of them, but the halves of them. And it's going to reroute it through what's called a channel purification. So this, a channel is, we think of it as noisy, but you can always view it as just, running a unitary operation on a larger system and throwing out some of the part of the state. Okay. So this is a unitary purification of the channel, and it just runs the unitary, and it just gives an output state. And here I'm just labeling the division of what's in system A, what's in system B. And the fact that the channel is assumed to be polynomial time computable means this whole state that I'm describing here, alpha 0, is computable in polynomial time. So this is alpha 0. Alpha 1, the second state, looks much simpler, and you're just applying the channel to just one entangled state. And this is also a polynomial time computable. And really, what's you don't have to dwell so much on all these this diagram, but kind of the intuition is that these two states satisfies Uhlmann's theorem, and it really says that by applying this random unitary R, you kind of decoupled the channel. You can think of applying the channel. It hasn't really applied the noise to the information you want to send across. So that's quantified by this theorem. It says that the marginal states of alpha 0, alpha 1 are the same on system A. So you can apply Uhlmann's theorem. There's a unitary U acting on the complement, mapping alpha 0 to alpha 1. And this unitary actually is a good decoder. And since we're assuming that Uhlmann is in unitary BQP, this means this encoding and decoding procedures are efficient. All right, what about the other direction? So now let's assume that Uhlmann is not in unitary BQP. Now we want to argue that this noisy channel coding is not performable in polynomial time. Okay, so the assumption Uhlmann not in unitary BQP, I argued a few slides ago that this is equivalent, or at least implies existence of a quantum bit commitment scheme. So we're going to use this to create a hard, noisy channel. But we're also going to assume that this commitment scheme is has a property of being non-interactive. Okay, so there's polynomial time computable state psi 0, psi 1, where to commit to a bit B, the committer is going to pick one of those states corresponding to the bit and send half of it. And then the reveal phase, the committer will just send the remaining half. Okay, so there's no backwards communication from the receiver. It satisfies its computationally hiding, meaning that the receiver, when it gets the B register, the B system of either of these two states, in polynomial time, it cannot distinguish between whether it got psi 0 or psi 1. Even though if it had infinite time, it could distinguish, but restricted to polynomial time, it cannot. So this is called the computational hiding property. So we're going to use a commitment scheme like this. I'm going to now construct a kind of a weird quantum channel, and it maps 1 qubits to many qubits. So it's going to take its input qubit, which it'll interpret as a bit B, and just generate a commitment, a quantum commitment to B. And then it's going to output the commitment register and discard the reveal register. And really just, you can think of it, what the channel is doing is just encrypting the input bit and just outputting this encryption. Okay, so here's a claim. In some sense, you're getting some scrambled version of the input bit, but it's not, I mean, if you had infinite time, it's not really, there's no noise added. It's just being mapped in some weird form. So the capacity of n copies of this channel is k, right? If you had infinite time, you can actually send k bits across k copies of this channel. On the other hand, if you're restricted to polynomial time, you can reason that there's no way that you can unscramble or decode this information without breaking the security of the underlying bit commitment scheme. So this gives an example of a noisy quantum channel where you don't expect to have polynomial time encoders and decoders. All right, so this is a sketch of the equivalence between Uhlmann being easy and noisy channel coding being easy.
Possibly something similar is true, right?
Yeah, I actually
use a channel for gargle, probably also something that people prefer.
Right. Yeah, you can run the same proof to argue that like a classical commitment scheme shows that this is hard. I actually don't know about the upper bound though. So whether you can achieve capacity, assuming that, well, I don't know what computational assumption you need to assume that achieving capacity is doable in polynomial time.
The channel is efficient and you can convert it. But you will define it. Whatever this model, yeah.
Right. Right. Yeah. Yeah, I think that's. But the encoder would just be the. What would the encoding be?
So we have to make some assumption that circuit.
Mm-hmm.
If you draw the circuit that has either drop some bits or has redundancy.
Mm-hmm.
You cannot do it. Given an output, you know how many came.
Yeah. Yeah. So yeah, I imagine there's probably a similar result classically. Okay, so that's basically it. I won't have time to talk about black holes in this talk, but there also is a connection there. But let me just wrap up and sort of summarize. I started off by saying, I think we need a new framework for reasoning about unitary complexity theory. And because traditional complexity theory has a hard time reasoning about these inherently quantum tasks. And so I think these notions of unitary synthesis problems and unitary complexity classes are better suited for understanding these things. Right. And so today we've seen sort of an example or illustration of this via the Uhlmann Transformation Problem. Captures the complexity of quantum commitments, noisy channel coding, a notion of zero knowledge unitary synthesis. So here's what the unitary complexity landscape looks like so far. And there's not so many things in it because we're just starting to define these things. But we have unitary BQP, unitary SEK, unitary P-space, and we can populate these unitary complexity classes with some interesting natural problems. And you might be wondering, what is this average business going on? And so far, we have a much better understanding of these classes when we think about solving problems in the average case, where the input quantum state that you're trying to transform is sampled from some distribution. What happens if you take away this average case condition? I'm not really sure what's going on there, but it's sort of interesting things to think about. Yeah, and I think there's many interesting directions to explore, right? Like we have this new complexity theory, and we can start playing around, like defining new unitary complexity classes. You can think about, is there a notion of unitary QMA, right? Which is like the unitary version of NP, and start saying, well, what are the relationships between these different classes? What sorts of interesting problems are in these different classes? I think another really interesting motivation for exploring all this stuff is because I think it's connected to the foundations of quantum crypto, right? So we have all these new quantum primitives that are coming out, like quantum money and unclonable quantum primitives, quantum bit commitments, and so on. And we don't have a very good understanding of what's the hardness of breaking these primitives, right? You can ask, is there, for example, a minimal complexity assumption needed for all of these objects, which is not known. And finally, we'd like to relate this new complexity theory to traditional complexity theory, right? So there's this question that is Uhlmann contained in unitary BQP given oracle access to a classical P-space oracle, or even an oracle for solving the halting problem, right? Or can we give evidence for or against? All right, so that's it.